Hi, and welcome to Lecture 2 of COSI 5785. Today we're going to look at an example of how a compiler might operate over sort of the whole cycle the compiler performs, starting with the source code of a language and ending with the generated code that the compiler produces. And so the idea is to give you an overview over the course and see how the various phases interact with each other to go from the source code to the generated code. So we'll use this very small example throughout the lecture. It's a piece of code in some language like Java. It should be familiar to all of us here. So remember that the input to the compiler is simply a string of characters. So even though you and I look at that piece of code and we see structure, the compiler doesn't see any of that. It just sees the list of characters involved. So the first step that the compiler needs to perform is lexical analysis. In a lexical analysis, what the purpose of lexical analysis is for the compiler to interpret or to read in the stream of characters that make up the input and divide it up into lexically important entities called tokens. So here's an example of how that might go for the lexical analysis of this piece of code. This list of things here are what we call tokens. This is what the lexical analysis of the compiler would produce. So now what we've done is we've gone through and, for example, found the characters WHILE, recognized that as being a reserved word in our language, and emitted the token T_while to indicate that. Notice other things have happened, like the white space has been removed. And so the output of this is simply this sequence of tokens, which are meaningful entities in syntactic entities in the language. After this lexical analysis, the next step is syntax analysis, where the input is this sequence of tokens that we're looking at here, and the output is a structure that shows the syntax of the language. And in almost every case that we'll talk about, that structure is called a syntax tree. So here's an example of the syntax tree that what we might construct during the syntactic analysis of this example. Notice that it shows the structure of the input. It's sort of getting us back to where we were, in the first place, in the sense of what you and I saw when we looked at the input on the screen at the beginning, right? So it shows that there's the most significant structure here is a while loop, and it shows that the while loop is made up of two things. It's made up of a condition, and it's made up of a sequence of statements inside of the body of the while loop, right? So the thing on the left there is the condition showing that y is less than z, and the thing on the right is a sequence of statements, each of them being assignment statements. So from this kind of a structure, this is the result of syntax analysis, the compiler would move on to semantic analysis. So the kinds of things that are done during semantic analysis are to analyze the tree and look for various patterns in the tree. So here's an example of one kind of semantic analysis is done where we're doing assignments of types to the different pieces of the syntactic structure. So, for example, we see from this analysis that the condition is a binary comparison, and there's a left-hand side and a right-hand side. Both of those things are integers, and the resulting expression is a Boolean. And you can see the similar kind of analysis being done on each piece of this tree. Many other things are done during semantic analysis that we'll discuss at various times during during the lectures in this class. But the next step after this, whatever the semantic analysis produces, is to generate the intermediate code, or IR generation. So for this example, the IR generation of intermediate code might look like this. The fact that we have a loop, and each of these statements that is produced are statements in, at the moment, a fictitious intermediate representation. But the point that I'm trying to illustrate here is that each of these statements are fairly close to assembly code or machine code for some. You can imagine them being close to the assembly code or machine code for some processor, but they're also high enough level so that they're convenient for doing various other kinds of reasoning. After we generate the IR code, the next step is to optimize it. So all that happened here, maybe was hard to see, is that, or all that will happen here, is that the loop, during the optimization, we note that A and B are not changed inside the loop. And so there's no reason for the x equals a plus b to be included in the loop. So a typical kind of optimization here is loop extraction, where that statement x equals a plus b is removed from the loop. And of course, there are lots of other kinds of optimization, but this just illustrates one kind. Okay, so then after the optimization, which by the way I pointed out earlier, it's not necessary to do the optimization. The IR code that's generated in the previous step is executable as is, and it produces a correct program. But the optimization, of course, makes the program more efficient. And almost all modern compilers do a lot of optimization. So then the next step is to generate code. Okay, so now this step shouldn't be terribly difficult, right? Because the IR code is already fairly close to the object code or the target language code that we're trying to generate. But here's an example of what it might do. Right, this might be the assembly language of some particular chipset. Okay, and finally, it might be possible for us to do, for the compiler to do further optimizations based on the fact that we're now in the actual target language. And so that would be this final step here, where you might do optimization of the code that was generated. So what was done here was that for it to realize that it didn't actually need to have that skip less than statement. Okay, we'll see you next time.